Hello. All right. Welcome back from lunch. We are going to get started. I am pleased to introduce Ankur from Meta, who is going to be talking about Project Flare and the work they're doing with gluten.
Thank you. Hey guys, my name is Ankur. I'm an engineer in the batch compute team here at Meta. Been at Meta in batch compute team for the past 7 years. For the past 1 year, a little less than that, we have been working on veloxification of Spark workloads. So today I want to take this opportunity to talk about the work we have been doing, the challenges we have faced, and our journey so far. So in terms of agenda, I'm going to introduce our team. I'm going to talk about our motivation for veloxification. We'll talk about how we got Gluten to Meta. Then I'm going to switch gears and talk about the migration that we are doing. As the mass migration, we want to make this offering transparently available to customers. We'll be talking about challenges. Of course, migration at this scale is many halves, sometimes many years. So we want to talk about how we are thinking about that, how we are working with Gluten, some of the improvements we have made. And finally, last not the least, we want to talk about AI acceleration, the new tool, the new shiny toy we all have to work with. So I'm going to talk about how we are looking at that and trying to speed up the migration that's going on. So we are the batch compute team. We provide Spark as an offering to all the teams within Meta. We are a single warehouse. So anyone with analytics need who wants to run Spark, they kind of funnel through us. We get to see large volume of workload. We get to see large variety of workload. So PySpark, data frames, SQL, you name it, we have it. More importantly, we get to see people pushing the envelope of Spark, what Spark can handle. So people who have worked in Spark would know that Spark is kind of like, it's not an infinitely scalable system. Driver is the single point of failure. There are things that start happening as soon as you have large number of executors, as soon as you have large number of tasks, as soon as you have large number of partitions and shuffle partitions, right? So when people come in and they try to push to the extreme to like tens of thousands of executors, we start seeing RPC bottlenecks. Sometimes they work with tens of thousands of partitions and millions of files within those partitions. All this metadata is huge, and it kind of like creates a memory pressure on the driver. And when the best case that happens is the memory pressure causes an on the driver side. But worst case, we start seeing RPC bottlenecks, and we start seeing things which don't make sense, and driver's not giving up, yet it's not really working. So we start seeing executor heartbeat failures and stuff like that. So for these reasons, we have a heavily customized fork, so we have lots of these fixes that we have applied for various different customers. We also have a mini ecosystem, might not be a surprise to people. We have our own distributed file system, our own metastore. We have file formats, our own table format. We have our own resource manager, which is Yarn-like. So all of these integrations give us a flavor of Spark, which is heavily customized internally. I want to talk about the motivation for veloxification. So the reason we are doing veloxification is twofold. One is efficiency. I think this is the obvious one. Of all the experiments we have run, we have seen like a 20-25% average win. We have, of the pipelines we have onboarded so far, the win is varying all the way from 20% to 70%. And when we see something as big as 70%, it's kind of exciting and boosts our confidence in the kind of costs that we can save around here. At our fleet, which is quite big, I don't know if I can talk about numbers, but we kind of believe that we have one of the largest fleet on the planet. These savings are immense. So we are talking about hundreds of millions of dollars here, and that's the kind of money nobody wants to leave on the table. So this is kind of like the obvious reason. But if money does not excite us, there is also enablement. There are some use cases which are looking for runtime and efficiency speed up. They have the sensitive landing time requirement, so the job has to be done. Cases like model freshness. And if we can speed things up for Spark jobs, we are effectively enabling these use cases. So that's like, we have a lot of AI ML workloads recently coming in with these sensitive requirements, so we are trying to help with that. Talking of that, if we think about scalability, we can actually enable those cases using two ways. We can horizontally scale, so we can always throw money at the problem. We can say, hey, we are just going to throw a large number of executors. We don't care about the cost as much. It's okay to have somewhat higher cost, but we really want this job done in n minutes or n hours. But we start seeing bottlenecks in driver that I talked about earlier. Now, these are not completely unsolvable bottlenecks. We are talking about improvements in event bus. We are talking about efficient memory utilization of the metadata structures we have within driver. So these are solvable, and there's a set of people who's working on these horizontal scaling problems. We are specifically focusing on vertical scaling. So vertical scaling, we are trying to help use cases which don't really need 5x, 10x kind of boost. Even if they can have 20, 30, 40% speed up, they're still going to benefit. These are the use cases which are there on the fence, and little push is going to unlock them. We're also talking about pipelines which are cascaded. So these are pipelines one after the other, and shaving off 20% from one pipeline across many pipelines is just going to give us that big boost that we are looking at. So with that, let me talk about Gluten and what it took for us to have the MVP around Gluten. As I mentioned, we have our own ecosystem. So one of the challenges for us is to get these open source technologies and make sure it's working nicely with all the integration points that we have. Right? We have our own file formats, so we had to build some integration into making Gluten aware of it. We had to do some integration with the distributed file system that we have, so integrating the access tokens, security, and remote spill support in there. One thing that we were waiting on was Spark 3.4. So we are in the middle of this migration from Spark 2.4 to 3.4. We had been using Spark 2.4 until last year. Things started changing. And last year, mid last year is when Gluten really got unlocked for us. So we have 3.4. Now we could take Gluten. Gluten has this hard dependency on 3.x because it's based off plugins which were introduced in 3.x. So last year is when we got started. So July timeframe is when we got started on this. We also have our own shuffle system, so we had to make some integrations with shuffle. We had to make Gluten aware of some of the things that were going on with our own shuffle layer. An example of this is the server-side sorting we do in shuffle. So when the reducer state starts, it already is getting the sorted stream, and there's no point having sort, but we found that Gluten wasn't aware of it, so we had to make Gluten aware of the sorting that's already happening. So this is like one of the few examples that we have had to solve. One thing we did around DevX, and I don't know, I think it's an industry problem, but kind of profound here. We have a large number of configs in Spark. We have like 2,000, 4,000 config knobs in total, and sometimes we pass these jobs around with 25 configs, and we say, hey, how do you run this job? You're like, take these 25 configs, go run the job, and people come back saying, this doesn't run. We're like, hey, did you look at that 17 config? Maybe there's a typo in that. So we wanted to be sure we're not spending time in trying to troubleshoot these issues, which take like maybe sometimes a couple of hours, and that really adds up and kills the productivity. So one thing we did early on was to invest into DevX, make sure that we have strong tooling, make sure that it was flip of a config for us. So we were able to enable this. This really boosted our experimentation velocity, and we were able to do it with ease. Lastly, I'm going to talk about the DSV2 writer, something that we had to implement. So in our 3.4 version, we have a heavy reliance on the override partitions dynamic exec. And we found this implementation was unavailable in Gluten, so we had to go implement it as part of Gluten. So we implemented that. Talking of the DSV2 writer, for people who are acquainted with override partition dynamic exec, or even if you're not, this is kind of like the high level of how it works. It has two parts to it. First off, it's not an operator, it's a command. It's a command which is going to dispatch these tasks. And effectively what we are saying is that give me the child plan RDD, and I'm going to pass you a function, and this function is going to process the rows which are created. In case of override partitions, all we have to do is write the rows. So RDD spits out the rows, and the override partition dynamic exec write to file task is going to write those rows in a file. When all these files have been written, there's some kind of commit that happens in driver, and there are multiple steps that happen in driver. We commit the files to the relevant directory. This is the partition directory which is going to be registered. Then we publish the partition. We compute the stats and publish those as part of the partition. There are things like empty bucket file creation. We also have small file compaction. So a bunch of things that happen, and there's like non-trivial complexity which happens outside of what runs on the executor side, right? So as part of our implementation, we wanted to be sure we are inheriting the logic, and the way we implemented this operator was twofold. We created the operator as part of the native plan, so it would write to files via the native plan through Velox boundary. And on the driver side, we would still have everything inherited. So any changes here, any fixes here, we don't basically have that code sync problem. We are keeping an eye on it. This is something that we want to contribute back to Gluten. So we are keeping an eye on it, and I think there's some development, but this is on our roadmap. Alrighty, so by this time, start of this year, we had this MVP that we had taken to multiple pipelines, and these pipelines, we are not talking about toy pipelines, but just like one stage, relatively complex, expensive, impactful pipelines. So we were able to demonstrate confidence of the MVP that we had. Now the next problem we are working on, starting 3 months back, is how do we take this, how do we deploy this at scale to all our customers? How do we do it in a non-disruptive fashion? How do we do it transparently so customers don't even know there's a migration going on, right? What we are looking at is sort of the high-level view of the migration framework that we have. So I'm going to read this from the bottom right. There's a Spark driver, which is trying to make an admission decision. So this driver wants to make a decision on whether this app should be running native or vanilla. It's going to need some kind of persistent state lookup. So we have a database maintained, which is going to have some kind of migration state. So every pipeline is going to hop these states, depending on the testing we have done before. Driver is going to make this lookup decision of the pipeline, and it's going to see, oh, this pipeline is blessed for migration. I'm going to proceed. There are more fallbacks which are implemented as part of driver. And one reason to implement admission logic in driver is because we have a lot of context. So we have context of flattened configs. We have context of runtime. The driver can go look up the history of the job to see if there have been failures, if the failures have been introduced by migration. It can see if there has been a cost regression. So out of being defensive, we take a lot of rules into account when we are doing enablement. And admission logic is only going to admit when everything looks fine. So working backwards, how did a pipeline get to the migration state? How did we bless the pipeline? There, of course, has to be a rigorous amount of testing that goes in. So as part of our testing, we have this A/B testing framework, which is going to fire off one run with vanilla, that's the control run, and it's going to fire off another run with native. And then we are going to fire more jobs to compute the hashes of these output tables. And we compare the hashes. Everything looks good across a couple of runs. We declare it a win. This is good to proceed. I'm abstracting this a little bit. There are a lot more checks with respect to number of containers, kind of task failures. If everything looks at par between the two runs, we are going to make this happen. Now, there's a problem with capacity. The problem with capacity is at our scale, there's only a limited fraction that we have, right? So how do we make sure that we are not shooting in the dark with respect to testing? And how are we making sure what we test has a high conversion possibility? We don't want to be in the business where we take all these pipelines, just throw and hope something comes out of it and try it over and over again and see that we are not really getting conversion. So we want to try and get to the plans which are within reach. which brings us to the shadow planning rollout that we did. So as part of shadow planning, what we did was across our fleet, we deployed this. We deployed gluten-only planning. On the left is how the run looks like. So in vanilla, we are going to go through analysis, optimization, planning, and finally, we are going to submit to DAX scheduler. There's, of course, the AQ complexity. We're going to do it stage by stage. But if you abstract that out, we are effectively doing the same with a Spark session, which is running with Gluten enabled. So this Spark session is a clone session. It's working in the background. We are not blocking the main thread. We are not introducing any latency challenge. And we are collecting all the fallback information as part of the planning itself. So right now, we have our production data sets, which are fully decorated with the fallback information, giving us a sense of prioritization, giving us a sense of score, giving us a sense of confidence that if we take these pipelines which don't have any fallbacks, there's a high likelihood that we would be able to onboard them. So as part of this, this is what we found. The data set that we have decorated, about a fourth of that data set has seen no fallback. So this is a fully nativizable plan. This makes us confident. This makes us very positive of some amount of footprint that we can cover without really running into conversion penalties. And some talks have talked about row to columnar and columnar to row steps that are injected whenever there are fallbacks. Our goal is not to run with hybrid plans. We are going to try and run everything native. So our push is to try and get to fully native plans as much as possible. The 47% share is coming from Java UDFs. So we have seen that Java UDFs come in the way. They are the sole blockers. What I mean to say is that if we can solve those Java UDFs, if we can migrate those as native UDFs, we would be able to fully nativize the plan. So we are not going to have that conversion penalty just because one of the project using scalar UDF is not compatible. So with these two, we would be able to cover 75% of the SQL workload. Lastly, 27% is coming from a flavor of UDFs we have where we are running these script transforms. These are like script and sidecars which are running out of band. This is not something we are tackling right away in the next 2 months, but this is something that we have plans for. We are looking at different approaches. At the end of the day, these transforms, these are like C++ transforms which adhere to some interface, and the task is to kind of like build an adapter so they can adhere to the Velox UDF and kind of like do some adaptation over there. All right, next big challenge. So we are basing our migration on the fact that we are going to have fully native plans, but is that sufficient? The other big challenge is that of memory and tuning. We can, of course, take a pipeline. We can migrate it, and we can try running it with Gluten, but it's not necessary that it's going to run reliably. It's not necessary that it's going to provide the efficiency and the wins that we are thinking of. There is some kind of memory tuning that has to happen based on the fact that we are switching the eval from something which is heap hungry to something which is completely off heap. So we have to make that adjustment somewhere. What we are looking at is the existing memory tuning framework. This is how we do the memory tuning around here at Meta. So we have a mix of user configs, history, and a new kit on the block which has been implemented recently. We internally call it memspec. It's a plan estimator. Think of it like a visitor which is going to walk down the plan tree, asking every node what the requirements are, and then do it at the stage boundary, finding out the max of all the different memory knobs and that we have to configure. So different kind of, there are like 5 or 6 different kind of memory configs. Heap and off heap are the most interesting ones, but then we have sidecar processes, we have Python UDFs, we have netty memory, and all of that combined gives us the container size. So in the end, when we are asking for containers from the scheduler, our equation kind of takes all of these memory configs into account and asks for a container. So for us, most of the problem gets simplified if we can have the adjustment between heap and off heap. And if we can work with the constraints that are total heap plus off heap is going to be constant, we can say with some confidence that our container size is going to be similar. So that's the amount of memory we are hogging on our clusters. And if we can hog that amount of memory for a lesser amount of time, we are effectively improving the cost. And this kind of aligns with all the experimentation we have done so far. So the work we had to do here was to make our plan estimate logic aware of the native operators. There was some complexity related to AQE. Might be too much in the details, but our plan estimator is tuned to look through the AQE plan using AQE helpers. But the way Gluten operates, it operates at the the preparations level, and it comes in as and when stages are getting progressed through AQE. So sometimes you would see the plan where the leaf stages have been nativized, but the subsequent stages haven't really been nativized, and that's because they're just waiting for AQE to kick in. All right, so in terms of top blockers, Java UDF is something I already talked about. This is the top blocker. We already have a migration plan for this. We have a flash talk later today where we talk about how we are using AI to accelerate the migration of these Java UDFs. Our strategy is to nativize all these Java UDFs and make sure we don't have any fallbacks. Script transformation, I talked about the adapter approach that we are taking. And last but not the least, I'm going to talk about this scan-only mode, which people who are working in Gluten might have some acquaintance with. This mode in Gluten just nativizes the scan operator. And given that most of the scans are columnar anyway, there is a columnar to row conversion happening no matter what. So there's no regression with respect to conversion happening. For us, this is an attractive option because even if we are not saving cost around here, we are still working towards the goal of stack consolidation with respect to redos. We are a complex stack. Most of the meta is C++. We have moving data infra slowly towards C++. Spark is sort of like the long pole to it. So we have these Java redos, and they come in the way of deprecation. So what we are trying to do is we are trying to have the scan-only mode where we are able to move away from these Java redos and have native redos. So this option is coming in handy. It's going to come in for workloads which we would not be able to fully nativize, but knowing that something exists in a toolbox is kind of good and makes us confident. All right, let me quickly talk about the Gluten improvements that we have made. So first one is around the driver memory. When we started off with experimentations, we found that driver was actually bloated. In some cases, it was taking like 34 gigs as opposed to 12 gigs in vanilla. We found that there was an inefficiency in the Gluten partition. So in terms of split generation, we are going to have these split objects and partition objects, as we call them in Spark lingo. And they have file metadata within. So there were two things going on over here. One is that we were not keeping the heap structures, which could be cross-referenced, having single graph, which is accounting for the memory. We were keeping serialized structures. So they were duplicated across the partitions, and that was spiking driver memory. The other one was around a large number of partitions and a large number of files creating large amount of metadata. So these partitions, if you peek inside, if you look at the file paths, these are relatively long file paths, and they are really redundant. It's only the file name that changes. So we implemented this mini encoding, which is going to pull the prefix, store it once per split, and not at a file level. And given that these splits can have hundreds of files within, we end up saving like 100x right over there. So this kind of helps with those drivers which are overshooting memory. DSV2 writer is something I already talked about. I'll just breeze through it. AQE plan splitting was something unique, which was happening for our DSV2 writers. So we noticed that the AQE plan node was coming in between and creating a fragmentation issue between the plans. So we would see that the native plans, there were two separate native plans getting invoked as opposed to one plan. So given AQE is kind of vestigial at this point, you're running the final stage and there's no other optimization that's going to happen. We implemented logic to kind of like throw away and make one single native plan. IO subsplits is an interesting one. With IO subsplits, we noticed that Spark would produce these splits. In some cases, these files were in gigs. And we would notice that we would have I/O prefetch and then followed by compute, and this was interleaved. So compute would actually wait on I/O. And Velox has this notion of subsplitting and prefetching, in which if you can provide it splits upfront, and if we can just break down that file into subsplits to Velox, it pipelines them and makes sure that the compute thread is not waiting. So we have a separate I/O worker thread, and we have a compute thread, and I/O worker thread keeps the compute thread busy every time. We notice like a 10 to 15% improvement with this. Finally, I want to talk about the AI boost. Got a minute, so I'll quickly breeze over this. In terms of development boost, the migration framework I talked about in the olden days would have taken like 1.5, 2 months. We were able to deliver it in a week or so. There's a table format implementation we had to do. It would also take like 2 to 3 weeks. We were able to deliver it in 2 to 3 days. So it's definitely speeding up the project in terms of features that we are delivering. But also our whole migration loop has been accelerated from this. So at this point, we have multiple skills which are assisting all the human loops that we have. So when humans had to sit on the edges and find out why the jobs are regressing, or why we have hash mismatches across these tables and figure out what is causing data corruption, now we have AI, which is kind of helping with that. So we have a bunch of skills. We are trying to get to a point where human is not working with the skills, but we are kind of like inverting this and have like automation and skill and pushing humans on the side and involving us only when it's really necessary for issues which are going to need issues like hash mismatches. There's an example we saw where broadcast hash journal was producing 0 rows. So something which really needs human intervention is where we want to keep ourselves. Otherwise, we're trying to automate the hell out of this. Cool. That's it from me. Thank you for listening. I'm going to be around. If you have any questions, we would love to talk about this. Thank you.